召集人张守进的大力的这个协助。那另外呢，我们要感谢台大光电所的黄建洲教授对博馆的的安排。另外呢，这个协办单位呢，我们要感谢我们这个工程中心台大光电所及我们这个荷兰贸易及投资就 NtuEE70th 的 financial support。那另外我们也要感谢中华光电协会及我们这个台湾 OSA 的这个 support。好，那我们大概我们就稍微再提下，因为我们今天的人数会比较多一点，所以我们下午的场次呢还在这个地方举行但是呢，我们提早半个小时，大概1点开始但是呢，最后的一场的这个论坛还是会在楼上时间照常。好，那我们首先我们要来我们邀请我们这个重要的贵宾那我们首先要邀请我们长期支持我们的研讨会的我们台大电子学院的的那个我们的陈院长。谢谢。
Thanks, Professor Chen. Ladies and gentlemen, it's my great honor to welcome each of you, especially for those coming a long way to Taipei to participate in this event, to join this very interesting conference. Our college, the College of ECS in Taiwan University, currently has 2 departments for undergraduate, EE and computer science, and also 7 graduate institutes, including the Graduate Institute of Optronics and Photonics and Optoelectronics, Graduate Institute of Electronics, Graduate Institute of Communications, which are very relevant to the main theme of this conference, and plus some others like EE, computer science, and so on. In total, we have about 160 full-time faculty members and 3,500 students, including 1,200 for undergraduate and 2,300 for graduate students. So our 160 full-time faculty members are actually working very hard and active in their respective research area. Actually, we have almost 30 IEEE fellows among these 160 full-time faculty members, so which is very good numbers. And today's topics, the C photonics IC, I believe is an area of growing interest, and I'm very glad and also feel very honored to see this event being held in this location. So once again, welcome to participating in this conference, and I trust you will have a very fruitful discussion and hope you have an enjoyable stay in Taipei. Thank you very much.
Chen院长The next important guest is the Mr. Wongter from the NtuEE, actually for his financial support. Welcome.
搞炸！给 DG Lau, Professor Chen, Professor Chang, Professor Lin, Professor Huang, Professor Lee, Professor Konen, Dr. Augustine, Professor Mortier, Mr. Wim de Boer, Dr. Liao, and Dr. Lin. All the distinguished guests, ladies and gentlemen. The Netherlands Trade and Investment Office is pleased to be a co-organizer of this event. The Innovation, Science and Technology Department of the NtuEE stimulates knowledge-intensive cooperation between Taiwan and the Netherlands. Photonics tops the list of the activities that we are working on. In October last year, Professor Chang and Professor Kuo, Professor Wang and other Taiwanese professors visited the Netherlands. They visited organizations like Technobis, Photon Delta, Dutch Optics Center, TNO, but also Smart Photonics and the Technical University of Eindhoven. Today, Smart Photonics and the Technical University of Eindhoven are represented here as speakers at this event. Tomorrow we will, with the delegation, visit Hsinchu, where we will visit ITRI, we will visit National Chip Implementation Center, and also we will visit UMC WaveTech. And already we are making plans for a larger photonics, integrated photonics delegation to Taiwan in November. When we are asked why we are so keen on the topic of photonics, then we answer, maybe it's a joke, but we say we want to lay the foundation of the next TSMC of integrated photonics. Now this sounds very ambitious, but then again, it were the Taiwanese and the Dutch who joined forces in the 80s to lay the foundations of what is today the world's largest pure-play independent semiconductor foundry. So today when we talk about waveguides at nanoscale, we talk about ring resonators, we talk about tunable lasers, and we talk about optical interconnects, then also please connect to this bigger picture. I wish you have a great day. 谢谢.
Actually, Monto have a Chinese name. It's called Ma Li. Is that right? 马是马上的马，力是力量的力啊。好，我们最后一个last important speaker 我们要请这个我们对我们光电学门有目共睹贡献的我们召集人，我们张守俊教授。
Well, good morning, ladies and gentlemen. Welcome to this workshop. And my name is Xiujin Chang. I came from the photonics program of the Ministry of Science and Technology in Taiwan. And we visit actually to Europe last year. We have a very fruitful trip. We have some discussion. And we believe that silicon photonics is one of the key areas that we should develop in terms of the MST in Taiwan. And in Taiwan, we have a strong 3-5-based photonic industry already. And we have LED and laser diode and all that. And we also have a very strong silicon-based integrated circuit industry, and the same in Europe, I think. And I think with that, I think we should be able to collaborate very well, and we should be able to learn from each other. And I hope this workshop will help us to build a bridge between us and the European country, particularly in Netherlands. And hopefully we can have a fruitful collaboration very soon, okay? And thank you again for your coming, and thank you, okay?
Thank you. So we are going to have a next session. It's very important. We have a 3 distinct lecture from the overseas. I'm passed to the Professor J.J. Huang for the, sorry. Actually, we have a because the a lot of people from the different, the locations. So we have some called the coffee break before we have some section. So we provide hopefully a good, the coffee break for everyone. So we have a take about until 10 o'clock.
请问一下，现场有那个台大光电所修课的学生吗？如果有修课学生的话，因为我们现场座位有点没有那么大，然后加上修课学生有点过多，所以我们有另外开了112的连线教室啊，你们可以麻烦你们就是往一些人往那边移动，谢谢。
So please take a seat. Our session will start. Okay, so welcome to the morning session. My name is JJ Huang from NTU. Today we have three distinguished guests from Europe. The first speaker is Professor Tom Kernan. He's a professor from Eindhoven University of Technology. He received his degree from electrical engineering from Eindhoven University of Technology. And then he joined Philips and later becomes the Lucent Technology Network System in Netherlands. He has been working with Lucent for many years, which he was in charge of. He's a technical manager in charge of forward-looking work department of Bell Lab within Lucent. And later he becomes a professor at NtuEE. His research topic is focused on high-speed multi-wavelength optical transmission broadband access network. Let's welcome Professor Kernan.
Thank you. Thank you for the nice introduction. Kaotsa. This should be ni hao or good morning. Yes, that's the one. No, that's my colleague. No, sorry, this is the one of my colleague.
Oh, no.
No. This one, yeah. Okay.
Up and down.
Okay, thanks. Let's get started. Okay, the title of my talk entitled Optical Systems Research in the Netherlands and the Role of Optical Integration. My thanks also go to the Dutch Organization for Trade and Industry for inviting me to give this talk and to the organization of this nice conference, of course. So I'm based in Eindhoven University of Technology, which is in the south of the Netherlands. And our group is part of the Institute for Photonic Integration, as you can see in the left part over here. So our institute, as you can see from the three circles, symbolizes the cooperation between materials research, which is actually the green area, devices research, and systems research. And actually, I'm chairing activities on systems research. So let me first introduce briefly our university. This is a picture of the campus of our university. We do have 9 different departments. We are a technical university, so all of these departments have something to do with technical sciences. And my institute, the Electrical Engineering Institute, is the one which is indicated here in yellow, which you can see in the back. We are housed in a very nice new building, including a very nice facilities for a clean room. This is a close-up picture of our department. So the building you see in the photograph, we moved into that one early last year. Our department as such is already existing for a much longer time. We have our 60-year celebration. Obviously we do education as well as research, and we have more than 1,000 students in electrical engineering. The staff as such, 350 people on the payroll, out of which the majority obviously are PhD students. We also have postdoctoral students. And our research in electrical engineering basically has 3 overarching terms. The one of the major terms is connected world, which obviously represents communication sciences. We do care and cure, electrical engineering, to provide services in the care and cure domain. And smart and sustainable society, that's about electricity generation and distribution, smart grids and so on. In all these activities, we favor intense cooperation with high-tech industry, both national, as you can see a lot of examples over here, like Philips and NXP, ASML, all well known to you, KPN's, the Dutch operator, as well as cooperation with international research institutes. Oh, wrong button. Okay, so my group, Electro-Optical Communication Systems, is focusing on research for photonics into communication systems. We are part of our department, Electrical Engineering, and we also are part of this joint institute for photonic integration. which you may know from the past as the Cobra Institute. Cobra existed since the early 90s of the last century, and recently, actually the 1st of January last year, it has been renamed into the Institute for Photonic Integration, symbolizing the stress, the emphasis we put on photonic integration technologies. So my group as such has 13 scientific staff members with a permanent position, around 30 PhD students and some postdoctorals. We have 4 major areas of research. The first area, and we'll go in more depth later, the first area of research is about ultra-high speed transmission within long links. Next topic is about routing optical data streams very fast in the network nodes by optical signal routing techniques and processing. Then we need to get down with all these high capacity to the user, so broadband access systems is a third area of research. And then the operation of all these network parts should be smoothly running together, so that's our end-to-end network management and control. So these 4 research tracks, I will give you some examples in the coming slides. But let me first introduce, because this conference is in the focus of integrated photonics, why we think that integrated photonics is a key technology. Well, we think it's not only for communications, which we are doing already for decades, but also for a lot of other interesting areas which are popping up, like sensing in medical for patient care, for smart industries to allow efficient production programs and manufacturing sites, terahertz, which is an upcoming domain, very high radio frequencies, which can easily be generated and processed with optical techniques. Safety and security is important, obviously, for the increasing security issues we have. Imaging, together with terahertz. Localization, especially for mobile applications. And automotive, like smart car driving. All these kind of things require sophisticated sensing techniques, and we have good hopes that optics is very important in that field as well. Gas sensing as an example of, in processing, and LiDAR between cars is also another application area which is of high interest. Well, what we are trying to establish, and that's an already advanced state of shape, that's the Photon Delta initiative. Photon Delta actually is the Dutch system in bringing research together with industrial activities. So it's symbolized in this picture by means of the 3 pillars. You see the green pillar actually symbolizing the research in the lower TRL levels, technology readiness levels, level 1 and 2. So that's where basic research takes place. That's in our university, as well as the University of Twente, which is in the east of the Netherlands. Within our university we have the Institute for Photonic Integration, which I already mentioned, so the joint research for materials, devices and systems. Within Twente University there is a similar institute called MESA Plus, which is mainly focusing on sensor applications using optical techniques. And then there's also the Polytechnical Saxion School, which has activities in photonics as well. So this actually symbolizes the pillar representing research. To the right, you see a large collection of companies in the Netherlands, which are highly interested in photonics. Among them is Smart Photonics, where Luc Augustin will speak after me. But you also see big names like ASML. You see Philips in there, KPN, and also a lot of smaller companies, all of them interested highly in photonic manufacturing and applications. So these are focusing on the higher TRL levels, 7 to 9, so to say. So really where photonics goes into the market. And what is now important is obviously to bridge the gap between research and industry. So that's where we are now establishing the so-called Photonic Integration Technology Center. That's actually in between. That should address the technology readiness levels 3 to 7. And that institute actually should focus on prototyping. So making the basic research results into prototypes, which then can be picked up by the industrial players. So in the middle, that's where the both parties are meeting, and they should have joint activities to bring this really to fruition. So the mission actually of the whole Photonic Delta initiative is to do the valorization of research and structured collaboration with smaller companies, SMEs, and industry. Well, some examples of Dutch photonic industry. There are quite a number of small, medium enterprises in photonics. Luc will talk after me and give an example of what Smart Photonics is doing. Other ones, Lyonics in the east of the Netherlands, focusing on silicon oxynitride technologies. Smart Photonics is indium phosphide. Phoenix Software making nice design software to design photonics, integrate photonics. We also have quite some SMEs which are using photonics already in the products. So Effect Photonics, which is making multi-wavelength lasers. Genexis for fiber to the home structures. We also have large companies like ASML, well known to you, Philips and KPN as the operator. All of these are highly interested and already busy with applying photonics in their products. Plus a large group of equipment suppliers, semiconductor equipment manufacturers like FEI and Tempers and so on, and assembly equipment groups. All of these are united in the Dutch photonics industry and closely connected to the Photon Delta initiative. So as the ambition we have from this initiative is to, to make a very close collaboration between all these three parties, supported by quite sizable funding from the regions in the Netherlands, really committed to make together a strong industrial infrastructure for photonic integrated circuits. Production, assembly and packaging are the key items in there. We are working basically on two major platforms, technology platforms, indium phosphide and triplex, which is silicon oxynitride. You see that quite a number of people are involved, more than 5,000, and the expectations is that this really will grow to big turnovers by 2025. And also sizable funding is being requested from the European Commission, which is happening right now. Eindhoven and Enschede are the main focuses of the photonic activities, and most likely it will grow all over the Netherlands in the very near future. Well, we will have shortly, actually next month, in the middle of June, as you can see, the World Technology Mapping Forum. That's an initiative which has been taken by Photon Delta together with AIM Photonics, you know probably the 600 million plus program in the US, addressing how to connect photonics to industry. So together there is this World Technology Mapping Forum planned, which will be in Den Bosch in the south of the Netherlands, with the aim to make a long-term roadmap for photonics. And in that World Technology Mapping Forum, the focus will be on the different technologies which are around today, so silicon photonics, indium phosphide, and the silicon oxynitride, and try to identify which technology fits best to which area of application, and when it will be ready for introducing in the market. So in the goal, the big goal of this total map is to put the roadmap in place for this Photonic Integrated Technology Center. The whole initiative is funded by the province of North Brabant, and you're all welcome to attend this one. Well, what we can see from research, I'm a research guy, but the prototyping effort as such is not only of interest to make the bridge from research to the market, but it will also help internally to support our research, and that's actually symbolized in this picture. IPI is our Integrated Photonics Institute, and the PITC is this prototyping institute. And you may recognize that in early research we are busy with the lower TRL levels, and it takes some time until the prototyping happens and we get more mature things, more mature materials. But when we go to devices, we need to build on stuff which is already pretty mature. So that means the TRL levels, the lower TRL levels from devices research are relying on the more mature levels of materials. And the same story for systems. You can only build systems with devices which are already pretty mature. So the prototyping phase in devices, for instance, is pretty important to get the system research started and being based on a solid ground. So that's how the interaction of the prototyping is also important, not only to the research, not only to industry, but also in the other direction to support internal research. So that's a key item we try to establish in this prototyping. Okay, let's now go more to the technical things. So our big picture of how photonics takes its place in communication systems all over the world is symbolized in this slide. You already know that fibers all over the oceans spanning the world. The transatlantic cables, 6,000 kilometers. Trans-Pacific are 9,000 kilometers, so very long distances, very high speed. So that's where optical fiber is in place already for decades. Going ashore, you get connections between the big cities, also hundreds of kilometers still, at very high speeds. But obviously you have now much more nodes in the network, which have to do very fast routing of your traffic. Going further down, you get to the city rings, the metro networks, where you have the big geographical areas of cities to be served. Further going down, you get down to the users, so that's where you get into the access network domain, and finally connecting to the houses. In that area, there's not only fiber, but that's much more still. There's still a lot of coaxial cable. There's still a lot of twisted pair installed, and obviously there's also a lot of wireless. And there is fiber to the home, for which in the Netherlands we already we have a quite nice penetration rate, but still there are a lot of other networks in place. So here the challenge is really to come up with very good, efficient solutions to drive fiber to the home all the way and to replace the other ones, in particular also to make a nice mapping to wireless service provisioning. So radio over fiber techniques feeding the antennas of the upcoming 5G networks, for instance, with fiber networks are quite important. And in our research vision, fiber to the home is not the end game. If you are able to provide fiber to the home, you have broadband up to your doorstep, but you still don't have it to your individual devices. So that means that we also have to come up with efficient solutions for broadband inside the home. We need to bring video services, telephony services, as well as data services, so the so-called triple play set, also inside the home via very effective means. And obviously we have lots of wireless devices in there, so we also need to come up with very nice fiber wireless solutions, so radio over fiber and so on. So these topics are all in the interest of research. Our research in systems domain is divided into 3 major tracks. So we have one track addressing long reach high capacity, talking about tens of terabits per second. We are talking about very fast packet switching in the network nodes, including the data centers. And we are talking about very efficient access to the user to serve a wide variety of services, also to cross various types of media. We have obviously to support mobility of the users. It should be low power because most of the user devices are battery operated. It should be low cost, obviously, and the services should be personalized. So that means also that you have a lot of diversity of your local traffic inside the home, which is quite different from the aggregated traffic statistics above. So it really requires a different research attitude. And we do have as a 4th track of research, network management and control, which is more based on harmonizing all the protocols for smooth cooperation across the network layers. Well, the total picture we have is called the pervasive optical systems. That means that optical will be everywhere, pervasive. So we will have photonic data operations within data centers, very dense interconnects, where integrated photonics plays a major role. We do have photonics for data transport, for ultra-high capacity. And we do have, as I mentioned, bringing all these broadband down to the user side. So as an example, for instance, you see inside the home over here, radio beams, but also optical beams for wireless connection to the users. With the goal overall, as I mentioned, uncongested broadband access everywhere, at low cost, obviously, acceptable for the end user, and moreover also at sustainable energy consumption levels, because ICT is consuming more and more energy, so we closely have to watch how to do that in a very energy efficient way. Energy efficiency with photonics, you can make serious contributions, good contributions to reducing energy. So overall, you know that, well, this is a quote already from Harvard scientists of a few years ago, that 1,000 Google searches consume as much energy as driving 1 kilometer with a car. And that's an American car, mind you. So that's quite a lot of energy, right? So optical communication technologies can do something to reduce that energy consumption. As a few examples, we can have quite sophisticated signal formats with modern modulation techniques, so putting quite a lot of information into a single transmitted symbol. So with a restricted symbol rate, we can still transport lots and lots of information. All optical packet switching is important within the data centers, because all optical packet switching allows you to avoid your electrical optical conversions at the edge of the routers. So that also helps a lot. Optical interconnects within data centers. By doing optical interconnects, you have much less crosstalk than you would have in copper interconnects. So in that sense, optical interconnects are important to reduce crosstalk, and as such, reduce the energy you need to combat that crosstalk. Fiber to the home. Fiber to the home is broadband which needs to operate 24 hours a day, 7 days a week. So it's quite important to make that very power lean as well. As an example, as you can see in the footnote, if you use VDSL technologies, you consume about 18 times more energy than you would do with GPON. gigabit passive optical networks. So fiber to the home is also important to reduce energy consumption. Radio over fiber is a very effective way to bring radio antenna closer to the end user. That means that the energy you have to transmit via the radio antennas can be much lower. It's going down with the square of the distance. So in that sense, you can also reduce a lot of your energy consumption. Well, the evolution of optical transmission as such, actually in the last century, in the mid-70s, people started with optical communication systems in the Chicago area. So that was the traditional intensity modulation direct detection systems, which actually got up to a few gigabits per second. The next stage of optical evolution came with coherent techniques, where you use local oscillator lasers to make your system more selective and more sensitive. So instead of binary transmission, you can go to more complicated signal formats. The era of dense wavelength division multiplexing was the next step in cranking up capacity and optical transmission. So that's where we really got up to terabits per second. And the latest step to go to the next level again is a space division multiplexing, where you exploit multiple modes within a fiber, which each of them create a parallel path of information. So that's the next stage, and for the moment we don't foresee what the next stage would be, but with this stage we're already going up to petabits per second, so that should be quite impressive. So integrated photonics plays a major role in this game. The latest stage about multi-mode transmission. Over here you see a chip which is able to launch the basic modes within a fiber plus the next order modes. If you looked into the previous picture, you could see that the fundamental mode, the LP01 mode, is the mode which is typically used in single mode fiber. But if you can open up the higher order modes, LP11A and 11B, then you already triple the capacity of a fiber, right? And this silicon circuit allows you to do that, because the constellation over here, which is 5 surface emitting gratings, you see a central one and you see 2 pairs which are orthogonally positioned. These combinations allow you to launch not only the LP01 mode but also the LP11A and the 11B into by a single integrated circuit. So we realized this integrated circuit. You can see the photograph over here, recognizing the 2 grating pairs over here and the two gratings in the other direction, able to launch these modes. And here you can see a provisionally packaged solution, where here you come in with 6 individual single mode fibers represented here in the left in the circuit diagram. So physically realized in the single mode fiber array over here, and then the few mode fiber catching all these individual modes is visible in this photograph, right? Well, based on these kind of techniques, we realized a system which was able to transport 255 terabit per second through this few mode fiber. A few mode fiber carrying, as I mentioned, the LP01 mode, the LP11A and 11B. Each of these modes is carrying 50 wavelengths. We also have 2 polarizations per mode, so that makes already 6 mode channels times 50 wavelengths times 28 gigabaud symbol rate per stream, and up to QAM32 modulation levels. All of that being launched into few mode fiber. And this fiber as such is not a single core, but it has 7 individual cores. And together, if you do your mathematics, you come up to your 255 terabit per second. And just to imagine what that means, that's enough to connect the whole world. If you take the world's population, which is 7 billion people, if you partition that into 2 parts, 3.5 billion on each side, and each one of these individuals is doing a telephone call at 64 kilobits per second, uncompressed, then you still have some room left to transport it to the single fiber. And the single fiber is a 7-core fiber. Outer diameter is only 192 micrometers, which is about 2 times a human hair, as you can know. So 2 times a human hair is enough to connect the whole world. That's reflecting the potential of integrated optics and fiber transmission in general. So what you need to build for launching these kind of fibers is symbolized over here. This is actually a glass waveguide structure where we made a configuration to launch these individual cores. Well, within data centers, we need very dense interconnects. Very dense interconnects means high level of integration. So you see some examples over here what we did in our labs, 3D optoelectronic chips, which allow you to make very compact boards, and these boards go together into a data center, allowing you to make low power consumption, high density interconnects. All optical solutions. This is a picture of an indium phosphide 16 by 16 switch, where the switching is done with silicon optical amplifier gates on the chip, operating at multiple wavelengths. And these kind of technologies allow you really to crank up the capacity of data centers without adding much to the power consumption. You see here a little bit more detail what is happening. So all these technologies together, 120 gigabit per second transceiver boards, are being realized as a parallel solution of integrated circuits. VCSEL array placement and packaging together. Well, I'm not a technology guy, but you feel from here that a lot of technology is being done in our institute to make this happen, together with lens coupling to make it very efficiently coupling to fiber arrays. And the major reasoning over here is that we want to get in today's data server boards, where you have your electronic processing, quite intense, somewhere on the board, needs to be connected to the edge of the board, so pluggable transmitters to make the connection to the outside world. But on the board itself, you often need repeaters or retimers to transport this very high capacity to the processing circuit, which is at some distance on the board. Well, the first step in making this more efficient is to move the optics over here closer to the integrated circuit, so you get mid-board transceivers. But obviously the best is to have this optical transceiver functions co-located with your electronics, silicon transceiver stuff. So transceiver together with your silicon circuit on a common carrier, and maybe later on a package. So that's the direction we are taking to make the data centers more effective. Optical integrated circuits for optical cross connects. You can see here the example. This is a switch which you already realized some years ago, which is happening on each port is dealing with 4 wavelengths, each of them connected flexibly by switching techniques, 4x4 switching, where the switching ports themselves are realized, the switching gates, with semiconductor optical amplifiers. So that has been realized up to 40 gigabit per second per channel in quite small footprints. Well, switching to closer to the user. So we all know that mobile traffic is really booming. So fiber networks itself need also to cooperate very closely with wireless networks. You can here see some prediction trends. Well, actually prediction is already reality, where Cisco predicted that the amount of mobile traffic is heavily dominated by video. It's increasing almost exponentially. And we also know that the major part of that mobile traffic is coming from indoor locations. So more than 80%, some people say even 95% close to that, will come from indoor. That means that wireless support from indoor locations is very important. So how to support that by optical techniques is, well, one of the big challenges. What we do see for today is that a gigabit per second indoor wireless is heavily getting congested. Radio spectrum is getting congested, so it's difficult to establish new radio links. You also have heavy interference because of the increasing density of wireless devices, and all of this results in quite high power consumption to make the system still work. Well, to reduce all these problems, the next step is to go to wireless picocells. Wireless picocells, which is the architecture for the upcoming 5G networks, as you know. In wireless picocells, we need to provide higher capacity per wireless device. The ambition actually for 5G networks is to go to 1,000-fold increase in capacity with respect to the LTE networks. So higher capacity per wireless device, which can be enabled by frequency reuse and spatial reuse. By going to picocells, you can considerably bring down the energy consumption because your antenna comes much closer to you. So downstream, there's much less energy to be spent. Moreover, also your distance to the antenna is getting smaller, so your device upstream will also have much less energy to spend. So it's much better for your battery life. Well, these picocells allow you to do dynamic capacity allocation, only allocate capacity at those cells where there is a traffic request, And by making these cells really small, you can do this at fine granularity, so that offers you a lot of potential to play around with capacity allocation. The downside, obviously, is that these kind of techniques become more and more complex. So that brings in the fiber. The fiber allows you to remotely generate radio waves and to bring these radio waves to the antenna sites along the fiber with this tremendous capacity. So fiber-fed picocells is an important architecture. These fiber-fed picocells, by wavelength routing, allow you to do dynamic capacity allocation on the fly, which is important. Moreover, by generating the radio signals remotely, you can concentrate all difficult signal processing on a central site and have the antennas only emitting the radio waves. The antenna sites themselves can be simple, and this way costs are reduced. Radio fiber techniques are essential to do that, and especially if you also introduce radio beam steering. Then within each cell you can make smaller cells addressed by individual radio beams. And the latest part, which we are doing research, is optical wireless communication, to replace the last radio links by optical beams. So I'll give you a few examples of those. So this is the picture we are pursuing for radio networks with picocell technologies, enabling the 5G networks. So you see here the picture of a big building with individual rooms, and within each individual room you will have antennas providing this picocell architecture, and each antenna is then feeding the mobile devices within that room by individual beams. So you need beam shaping and beam forming to make that possible. These individual beams are created with phased array structures, as you well know. So individual antennas, which need to be carefully controlled in the phase relation to make beam shaping and beam steering possible. So that's what we call the radio access point. That would be able to generate multiple beams, and each of these beams should be fed out of the central site, the home control center, which is actually the unit where you make the interconnection to the access network, and which provides the translation of access information into the individual radio networks inside the home. So by this kind of technology, we are able to offer quite high capacity per beam and also energy efficient operation, because you point the beams only there where they need to be. And optical beam steering, we devise techniques where the control channel for the beam steering is actually the wavelength. So the wavelength of each optical signal will determine where each beam is going to. So that means that your control, the wavelength channel, is embedded in your data channel, and that's also quite significant for system architecture simplification. To do this, we use true time delays in your phased array antenna, true time delays which allow you to really have broadband operation, and to do that optically tunable. And how we do that is actually this basic picture. You can see here a linear array of antennas. The linear array of antennas where we create the time differences between the antennas by means of this intermediate stage. This is an array to waveguide grating. That's a device where if you put in multiple wavelengths at the input, these wavelengths are separated over the individual loops, and each loop, as you can see, has a different length meaning a different delay time. So when you choose for a particular wavelength over here, you choose a particular loop, you get a particular delay time, and the next stage you get the same delay time and the same delay time. So that means that there's a strict delay relation between the antenna sites, and that delay relation defines where the beam should go to. So by just changing the wavelength of your laser over here, you can steer the beam. Moreover, the laser is obviously modulated with your information. There's both the wavelength and the data together take care of data transmission as well as the beam steering. So that's the one-dimensional structure. You can expand this into a two-dimensional one by a smart choice of your free spectral ranges of the arrayed waveguide gratings, and then you can do two-dimensional steering. So in this way you can go with a pretty advanced integrated circuit into multiple beam steering, two-dimensional. And this is the circuit which we realized. That's in this case done with silicon and insulator. So you recognize the individual AWGs over here, plus the delay loops over there. So this was a simple 2x2 case, and we are now expanding this into larger systems to make this as a very compact solution for wavelength controlled two-dimensional radio beam steering. Well, As a next step, as I announced, is to go into the optical domain for wireless connections. So that's where we look for replacing, if you like, Wi-Fi by optical. You probably know already visible light communication. Visible light communication, well, if you look into the radio spectrum as such is operating, well, in practice, you have ranges up to, let's say, 300 gigahertz, down from 2.5 gigahertz up to 300 gigahertz is about where radio people are busy with. Above that area, you have still very nice optical domain to open up, providing a lot of extra spectrum. And the near infrared, what we are already using in fiber communication, is also very attractive. The nice thing of optical spectrum, nice to the radio spectrum, is that optical spectrum is still unregulated. So you don't have license issues over there. So it is a very powerful domain to open up. And also applications where radio is not feasible or not allowed, like in hospitals, airplanes, manufacturing sites, and so on. That's very interesting for wireless communication. Well, basic structures for optical wireless communication, there are actually two families. You have visible light communication, where you can use LED lighting and modulate the LEDs to bring down information. Well, in that sense, you have LED lighting, which typically has a large footprint, and you have to serve many devices within that footprint. That's one solution. The other solution, which we are pursuing, is actually using beam steering. So we are not using widespread light, but we are using small rays of light, narrow rays of light, which each of them are addressed to individual devices. And as such, you get very high capacity beams, which you may say are like a fiber, but then without a fiber, right? So they are free space optical beams. And in that sense, what we are doing is to realize a system offering more than 10 gigabit per second per beam. Well, you may worry about the eye safety issues. Well, the human eye, as you can see in the left, is composed in the back of your retina, which is the most sensitive part of your eye. You need to be very careful that light is not damaging your eye, right? So when the light is entering, you first hit the cornea, then you have the lens, then you have the pupil, and then you have the vitreous body, and only after that one you get into your retina. So if you look how the different light components are reaching your retina, obviously visible light goes all the way up to the retina, so you need to be careful with power levels. That means that power levels for visible light are clearly down to less than fractions of milliwatts, right? But if you go to infrared communication, light is not reaching your retina, but it's stopped at the lens, and after that the vitreous body is absorbing everything. So that means that for infrared you are allowed to send much higher powers, up to 10 milliwatts is allowed without having any damage to your eye. Based on that, we use infrared. Moreover, we reuse optical techniques in there, optical fiber techniques, so that allows you to really go up to high capacities. So this is the system concept we have. So you recognize a similar picture as we had with the radio beam steering, but now we use light beam steering. So here you see a basic principle. We use two passive grating structures which are orthogonally aligned to allow you two-dimensional passive beam steering. And depending on the wavelength you put in, the beam takes its particular direction. So as you can see symbolized in the picture, every wavelength corresponds to an individual device. And that means you have independent high-capacity paths up to the device. With this kind of technique, we realize more than 40 gigabit per second discrete multitone over 2.5 meters. So that means 40 gigabit. That's, well, about one DVD with a video movie being transmitted within a second. And that's per beam. So this is a more extensive experiment, which for reasons of time I will not go into much detail, but you recognize here the two individual gratings, and the light part is folded by mirrors, but in this case it's like 3 meters, and here in this experiment 32 gigabits per second. Here you can see how the spots of the wireless beam are traveling across the area when you change the wavelength, so that symbolizes the coverage you can get. We reported at last OFC in Los Angeles in March, reported a bidirectional solution for this system as well, based on a slightly different technique with the fiber array and the lens structure, 2.5 meters reach, 35 gigabit per second downstream on off, and upstream with 60 gigahertz radio techniques. So it really shows you the great power we have at optical wireless. The next topic also dealt with at the OFC in a post-deadline presentation is on the receiving side. So how can you design an optical receiver which has at one end a large light catching area and at the same time having a large bandwidth? So typically with top illuminated photodiodes, there's a compromise to be taken between the area of collection and the bandwidth. But when you separate the light collection function from the detection function, so we have the light collection by surface gratings and the light detection by a waveguide photodiode, we can have a good solution for this compromise, where you can increase the optical collection area without affecting the bandwidth. So we translated that into integrated optics, which you can see over here. We have a surface grating to the left catching the light. This collected light is fed via waveguide to a carrier traveling photodiode at high speed, 67 gigahertz even. So with this solution on indium phosphide, we made a very effective, high aperture, high bandwidth optical receiver for optical wireless. Okay, that brings me to my last slide. The last slide is just to stress again that integrated photonics has an important role to play in realizing a very powerful optical systems. We have shown you that ultra-high capacity transport is a need coming up soon for 5G networks. So the spatial dimension in fiber by using multiple modes can be enabled by photonic integrated circuitry. Together with dense wavelength multiplexing, there you can really go up to petabits per second in a single fiber. Next to that, you need to address the ultra-high throughput in data centers, which you can effectively do by introducing photonics in data servers on the boards inside the data racks. So photonic integrated circuits allowing you to do that, dense interconnects at low power. We need to go down the user all the way, making a strong combination of wired networks together with wireless, and now also the Internet of Things. So dynamic radio over fiber techniques, and beyond that optical wireless. Also in that domain, photonic integrated circuits have a major role to play, which I did not address, but which is also evolving fast, is to have photonic integrated circuits for sensor systems, for the remote health control, structure monitoring, and so on. So that's another important domain where photonics, integrated photonics plays a major role. And with that, I would like to conclude. And thank you for the attention.
Due to the time limit, the session is open for only like 1 or 2 quick questions. Any questions? Okay, please.
Thanks for your speech. I have a question about vertical top illumination photodetector. Is there any required responsivity for this kind of photodetector? Because it's illuminated from top. So I think the active layer should be very thick to have a very good responsivity.
You're talking about this picture, or?
Top illuminated photodetector.
The photodetector as such, yeah. And this architecture, we are trying to optimize the light collection together with light detection and to separate these two functions actually. So the photodetector itself has a relatively small area. It's waveguide coupled.
Yes, but in page 35.
35? That's beyond my presentation, I think.
Sorry.
Oh, sorry, 35, sorry. Right. Yeah,
yeah, it's there is a top illuminated photodetector.
In this bottom picture, actually, it symbolizes that the photodetector stays the same, right? So it's just a photodetector which matches ideally to the waveguide. And that's a small one, just a few micron active area, which allows you to go up to 65 or 67, I believe, gigahertz bandwidth. But is this, I'm not sure, is this your question? Or?
Okay, thank you. I mean, the top illuminated, the top one.
Top one, yes.
Yes. What's the responsivity required for this kind of photodetector?
Yeah, the top one actually is symbolizing the traditional way to do it, right? So to have top illumination on your photodiode, And typically when you increase your collection area, you increase capacity, the whole photodiode gets slower. So that's not a solution for our needs. We need to have high capacity as well as high bandwidth, as high collection area. So that's why we come up with the second solution. And this one, typically, if you have photodiodes which are like 50 micron in diameter or more, well, you're easily having only a few gigahertz or less of bandwidth. And we need more to get to our 40 gigabits per second target, right?
So let's thank the speaker again for such a wonderful talk.
Thank you.
Our next speaker, Dr. Luc Augustin. He received the master and PhD degree in electrical engineering from Eindhoven University of Technology. After his graduation, he switched to industry, and now he is the CTO of Smart Photonics, very good companies that working for indium phosphide foundry service for integrated photonics. His expertise is in simulation and design of indium phosphide-based photonic integrated circuits, fabrication of refined photonics components, and integrated circuit and characterization of semiconductor photonic component. Let's welcome Dr. Augustin.
Yeah, thank you. Thank you for the introduction, and it's my pleasure and honor to give a presentation for you today. So thank you also for the organization and the invitation. So I will talk today on indium phosphide-based integrated circuits. So I'll tell you a little bit more about our company, Smart Photonics, who does the foundry work for this. So I'll tell you what indium phosphide can mean for photonic integrated circuits. So a short outline. So I will introduce Smart Photonics. I'll tell you about our view on photonic integration and our platform technology that we have developed, and also how you can access it. So a few words on Smart Photonics. We are a young company, only founded 5 years ago, but we have a very long history in lasers and indium phosphide-based photonics, dating back from to the 80s and 90s, where in Philips there were the high-grade telecom lasers were developed, this division was acquired by Uniphase, and after the bubble they left Eindhoven, and but still the people and the knowledge remained in the Eindhoven area. And actually together with Eindhoven University, steps were taken to develop indium phosphide-based photonic integration. And in 2011, Philips decided to stop the photonics activities, and together with Eindhoven University, Smart Photonics was founded in 2012 as a pure play foundry. So we do not have our own products, but we produce for others, and also focusing on indium phosphide, and mainly on focusing integrated photonics based on indium phosphide. So that's in a nutshell Smart Photonics. So where do we position ourselves? It's really in the manufacturing part of the whole value chain. So the design is really coming from our customers. I think you saw this picture coming by in Tom's presentation. So really the smart IDs, the concepts of new circuits are developed by our customers, either universities or small and even larger companies. And we will then do either proof of concept, so small series, and we can scale up to larger volumes in our facilities. And then we deliver in the end the finished chips, and our customer goes on and do the packaging and the testing and the assembly in the product themselves. So really focusing on the semiconductor part of the product and the manufacturing of it. So a few words on our facilities. Actually, we are in 2 locations in Eindhoven. One is the high-tech campus, is the former Philips campus. There we have a moderate-sized clean room in which we can do the production, and that's so we have both the processing capabilities, so processing the indium phosphide, as well as the epitaxial growth for the active and the passive layers that are required in the circuit. I'll tell you a little bit more on the technology later, but we can do the full epi and processing for the production in our own facilities at High Tech Campus. And then we partly use the facilities of Eindhoven University. One of the biggest important steps is they have a very high-end lithography tool, so 193 nanometer ASML scanner, so really high resolution that we can use for gratings on indium phosphide. And part of our R&D work is also done at Eindhoven University. So that's a little bit on smart photonics. So I will go a bit deeper on our integration platform. So we have what we call a generic integration platform on indium phosphide. So I don't have to tell you this, but for this audience, but we really believe in photonic integration. If we look back to what happened over the 30, 40 years in electronic integration, it really has changed the world. And most of it, so electronics is everywhere in your mobile phone. And it's mainly there because of integration, because you can make all the devices smaller and you can make it handheld, and that really changed the world. And we really believe photonic integration can do the same. If we can integrate lasers, if we can integrate a lot of functionalities on a single chip, that it becomes handheld, then you can integrate it in a lot of applications, as already been pointed out also by Professor Konen in the previous talk. But we really see it so not only in telecom where people know the photonic integration, but also in healthcare, in automotive, in machines, and these kind of applications. So we are really at a tipping point in history where photonics can change. It could be the next changing technology. It's not only us that believes this, that indium phosphide is important, but also if we look to the market studies, for instance by line counting, we see that the indium phosphide integration will take a big chunk out of the transceiver market. So we believe we are in a very good position with our indium phosphide platform for that. Yeah, so what we really believe is generic integration, as we like to call it, and generic integration on indium phosphide is the key to success for photonic integration. If you look to electronics, you have a few basic elements. If you know how to produce them very well, you can make a large variety of components of it. And the same can be true for photonics. If we know very well how to produce a waveguide, so how to produce a phase shifter, how to produce an amplitude or a gain section, so then we can manipulate a lot of properties of the light. So then with these elements, if we can define them as basic elements, then you can you have a tool set, a toolbox available for making integrated circuits. And so really that's what we did. That's what the focus of our company and our platform is on. It's really to make standardized industrial integration processes for these simple set of building blocks, so that people can use them on a functional level. You do not have to understand the semiconductors anymore. You can just think at a higher abstraction level. If you need gain, you can take a gain block from the library. If you need a waveguide, you can take a waveguide from the library. And together with the support from software design kits, you can really fast and accurately design your circuits. And that's really the key of the technology of this integration platform. What an additional advantage of, because everyone has the same technology, you can also have multiple users using the same technology at the same go. So you can have multi-project wafers, so that you do not have to buy a full wafer, but you can only access a few chips from a wafer, which is a very cost-effective solution for fast and low-cost prototyping. So that's another advantage, because everyone uses the same technology. And because we gain a lot of experience on running the same process over and over again for a lot of our other customers, we have a lot of knowledge on the process. Even on the multi-project level, you get to know the critical points, so you know the yields and the process capability for a specific product. So also scaling it up to larger volumes is much easier than that you have to start with a dedicated process from scratch. So those are the advantages of the generic integration platform. So this is what our implementation looks like. So as said, I think I will call the name indium phosphide a few times in this presentation, but once more, it's based on indium phosphide, which means that it's really the solution for a real monolithic integration of all functionalities. So we can integrate waveguides as well as phase modulators, as well as the lasers or gain sections, so semiconductor optical amplifiers can be integrated in the same process as the waveguide, so really monolithic. And using high-end semiconductor equipment for this integration, we can also learn from what the silicon world or electronics world has done for in the processing, and we can build on a strong and a mature technology for lasers, which have been around for decades in telecoms. So it's a mature basis to start from, and from that we can build our platform. And so we really believe this is an enabler for low cost integrated circuits, because we can in one go integrate multiple actives and passives. We do not have to pick and place, especially if you want to have complex circuits with a number of gain blocks, with a number of lasers all integrated. By having a monolithic solution that's very cost effective. And furthermore, which is a very important one, is that because we can integrate the detectors as well as the lasers, we can test the full circuit on wafer, so electrical to electrical. So we do not have to couple the light out to actually test some basic functionalities of the circuit, which is in a production mode is very cost effective also to screen in an earlier phase. So those are some of the advantages of our platform. I quickly go through the process just to give you a feel of what it is that we do. So everything, the whole process is based on wafer scale. So every step is done on a wafer. So we start with growing the active material, so that the laser material, basically telecom grade laser, is growing on a wafer. And we remove it everywhere where we do not need a laser and where we want to have a different functionality. So the most simple one is to grow a bulk waveguide layer to guide the light everywhere on the chip. And then we overgrow with a common top cladding. So at this stage we have a wafer on which active islands are present on the positions where we need to have amplifiers, or we need to have lasers. So this is all lithographically and monolithically integrated. The next step is then in the same wafer to etch waveguides. We planarize the whole structure, and we deposit metal. Planarization is done with a polymer to have a good RF performance, and on top we deposit the metal to contact. So this is really in a nutshell the process, just to give you a slight feeling on what it is about. So if we then look at the capabilities of the platform, I think a lot of you know all the nice things that we can do with integrated photonics. It's there's a lot of couplers, multiplexers, filters, phase modulators. This can be done on a lot of material systems, indium phosphide as well as silicon, as well as triplex or all kind of silicon oxynitride waveguides. Then if you can integrate modulators, then you can have much more sophisticated circuits. This can be both in indium phosphide and silicon, so you have phase modulators. If you have, you can Mach-Zehnder modulators, cross connects, all kind of circuits. But those are some basic elements. But then if you want to have lasers or gain blocks, then the only way is to use 3.5 still. It's so we can integrate in SOA. You can make lasers, you can make DVR lasers or multi-wavelength lasers, or all kind of different circuits. So this is just to sketch a bit the landscape. And that's also why we are focusing really on the indium phosphide-based platform. Of course, we have a generic integration platform, so with one core technology, but it's really a platform technology. So there's different flavors are possible of the same platform. So, for instance, the offering that we do in the MPW, it's I try to make it in a graphic here. So we have to there's an active layer present, which is really optimized for lasers. There's passive circuits are based on a standard waveguide layer. We can define gratings, and then there's the baseline process is below. But if we want to have a more high-end transmitter for datacom, for instance, then we have to have it operating at a higher speed. So we need to have a semi-insulating substrate instead of a conducting substrate. The laser active is still the same, but we have to introduce a phase section to have efficient phase tuning in the laser, and also for high speed modulation. Of course, we need gratings, and then the rest of the process is more or less the same. And yeah, so there's different options. If we want to have a receiver, we want to optimize the active layer a little bit more for higher responsivity and higher speed detection. So in this case, in this way, we have really a platform technology in which different flavors of the same process can be used, and which makes it very versatile for a lot of different applications. And even there's some degree of further customization is possible if people really want to have it at slightly different wavelengths, or they have their own epitaxial design. As long as it fits into our design rules, it can also be fit into this platform technology. Another important aspect of the integration platform, as we have developed, is the access for users to the technology, and to have an easy way of accessing the building block library. So therefore, together with some software parties, we designed a software library or process design kit, and that can be used for circuit simulation and also for mask design. Well, we have a design manual in place, and with functional descriptions of the building blocks, so that we have so you can you know what gain to expect for a certain amplifier if you use it. And well, there's a fuel layout aware design flow, which is very, very important for integrated photonics, because you cannot just connect different elements to one another, but you really have to keep the phase relation between the different components on the wafer. So really the length of a waveguide is very important as well. So we have to know when you're designing, when you're simulating your circuit, you have to take into account also all the actual layout properties of the devices, which is important. And together with the software parties, we managed to get this full design flow in place. So yeah, the access is really to a number of state-of-the-art software tools. So that's why Phoenix software, which is really focusing on the mask design part of it. So the layouting of VPI Photonics is a simulator which works well with Phoenix software. There's Photon Design is more on a physical layer, and a frequency domain simulator for the circuits. And then there's Nazca Design. It's a freeware software tool for doing the layout. And with all these software tools, you can make the design for our platform. I'll quickly show you a little bit on the layout aware design flow. So it's a collaboration of VPI Photonics, Phoenix software, and Smart Photonics to get to a full flow in which you can do a functional design using the parameterized building blocks that are in the library. And this makes it possible to have a fast and accurate modeling of rather large scale photonic integrated circuits. And by sweeping the parameters of the individual components, you can see what the eventual impact is on the full circuit design. And what is important is to keep really the orientations and all the connections and even the length of all the waveguides. They are kept in the simulation flow to easily export it to a mask design that can actually be fabricated. And here there's so some of the simulation results, and these are actually the measured results. And there's very good agreement in both. So really, this whole flow is being optimized now and tested, and the models are more and more calibrated to get this to a higher level. But the basic functionality is already there, so you can actually use this to design your circuits from now on. Yeah, so that was more on the platform, just to give you an overview of what it is. And I will now a little bit zoom in on the building blocks. So what is it actually that we produce? So here I stated some of the basic elements with the typical performance. I will not go into too much detail, but if you can have a look at this list, you see this. It's not really a compromise. It can meet specs that other technologies do as well, with the additional advantage that we do integrate the actives. So yeah, we have the waveguides. They have moderate losses. We have some optimizations going on at the moment, so we can really reach below the 3 dB per centimeter now. It has been a little lower and a little higher in the past, as I think Professor Young will will have noticed here. But at the moment we can reach these values reproducible. But yeah, and also the SOA gain. So the gain material is also it's really comparable to off-the-shelf components, and you can now with no extra cost integrate them into the circuits. Yeah, so a few words on some of the components. So there's the phase modulator. That's something that is currently being optimized. The device that is offered for free, so to say, in the MPW service or in the standard platform has a little more than 10 gigahertz bandwidth, and we are optimizing it further. We have an optimized design available that has a bandwidth higher than 25 gigahertz at a VPI of 2 volts, so which is really suitable for the next generation devices. And but yeah, at the moment, so this device is offered in the MPW. We have DBR gratings available. So they are currently in a test phase, but they are available to users to test them in their circuits. So we are continuously optimizing them and characterizing them. What we also, well, at the moment we still use E-beam for writing those gratings, as is rather common in our world. But we are also introducing now the ASML scanner, so to do really a lithography tool, so one shot for defining the gratings. And actually some of the results are shown over here, that we have a very reproducible grating performance over a large wavelength range and over the whole wafer. So there's really, this tool is suitable for scaling up to production. So it can do 100 wafers an hour, as well, if we compare that to E-beam, where you need a few hours per wafer. So that's it's really a dramatic improvement. So that really is making the platform ready to scale up to production volumes. Yeah, then the photo detector. So there's also we are optimizing it, but the device that is offered now has a responsivity of close to 0.9 amperes per watt and a bandwidth of above 20 gigahertz with very low dark current. So it's a nice detector that can be easily integrated into the platform. Yeah, so that was a little bit on the technology side. Another important aspect is the MPW service, so the multi-project wafers, in which you can easily and with a low threshold access the technology. So we started offering the MPW service. It was actually developed for photonics in a European project with the university and Heinrich Hertz Institute in Eau Clairo in the UK. And Smart Photonics adopted this technology as well, and we developed it with the university. And we were the first to offer it on a commercial basis. In July 2013, we had the first MPW run on indium phosphide for photonics. And at the moment, we run an MPW every quarter, so every 3 months you can access our technology, and it really gives a low threshold access to the technology. And we have a broker in place. It's called JAPIX. I think Professor Kone also mentioned it. They are located at the university, and they can offer easy access to the technology. They can help with taking the first steps into the design, and also helping getting the right software in place, and helping getting access to the technology from our foundry. Yeah, so what is another important aspect is really we did if we look at an analysis of the users of the platform, we really see that there's a shift from academia to industry. So it's not anymore a university party. It's really industry is taking up. So we have on every run we have a significant amount of industrial users that participate in the run, and ranging from SMEs but also larger companies who really want to use the technology and see what it can mean for them. So yeah, we have done over 10 runs in the past years. But actually this gives a slightly worrying message, but one of the things is that from I think from this run on somewhere we had really all the runs were completely filled. So actually there was more academic users coming in and keeping the same number of industrial users. That's why the percentage slightly drops, but in fact it is actually growing the total amount of users. So we really see that this uptake of industry is real. And yeah, what's good to mention is they are really coming from all over the world, from the United States, but also from Asia. Well, actually from Taiwan we have a user on one of our runs, so we are very happy for that. And yeah, so it's really taking up. If I then look a little bit more on the application areas, that's really supporting the hypothesis that it's not anymore a telecom or datacom oriented technology, but it's getting more and more attractions from different fields. So actually, if we look to our MPW, the main part is not anymore the optical communications part, but it's really it's focusing more on sensing. So either fiber Bragg rating readouts for all different applications, for a medical application as well, for an aerospace application we have on board. There's gas sensing and there's gyroscopes, and this is really the largest application. What's also nice to notice is that especially universities, they try a lot. So they have more a general process testing, so they want to investigate what it can mean from them. So that's also a different class of users that are available there, which takes up a big part as well. I quickly go to some examples that have been fabricated on the MPW platform. So one nice thing is that we managed to make a 100 gigabit transmitter just on one chip, just on the standard MPW platform. It was developed by a PhD student of the Cobra Institute in Eindhoven. And so there's 6 widely tunable lasers with a tuning range of 40 nanometers. And there's 6 Maxino modulators, and even 6 post amplifiers, and they are all combined with an AWG on one chip. And a 20 gigabit per second transmission, even 30 gigabit per channel has been demonstrated on this chip. And so this is just the standard MPW that is available for anyone. And by smartly designing the chip layout, we can with this technology have a 100 gigabit transmitter. A completely different example is for gas sensing. It's a mode lock laser. And this is a nice example. I always like to show it because it shows really the capabilities of the technology, where there's a this one chip. It's 2 by 2 millimeters, but there's all the components are inside. There's an amplifier. There's a saturable absorber. There's an amplifier. There's a very long passive cavity, and there's phase shifters to tune the exact cavity length. That's all in one integrated chip. And what is important is we get a very clean spectrum out of it. So that also the losses of the connections, so the butt joint connections of the active and the passive are very low. So low in reflection and low in loss. So that's why we can make a nice laser with a very long cavity. So this really demonstrates the capabilities of the technology. Another one that is a rightly tunable laser where there's an active section integrated with a cascaded Mach-Zehnder interferometer. This design is also from the Cobra Institute in Eindhoven. But with this, so it's a very complicated design, but if we can integrate it, it becomes really feasible to have a low line width and a very wide tuning range laser on one chip. And there's also, the main target here was again gas sensing, but it can be used for a wide range of applications. So this brings me to the summary of my talk. So I showed you our generic integration platform on indium phosphide, as we believe it's really the key to low cost and high volume integrated photonics. You all can get access to the technology via our MPW runs, and we have demonstrated already a large range of applications, and there's industrial scale production processes in place for taking this one to the next level. So thank you for your attention.
We have time to take one or two short questions.
What's the wavelength of your scanner and the wafer size? The scanner? The ASML scanner. It's a 193 nanometer device. So it can operate at 12 inch, but actually the special thing or the uniqueness of this tool is that it works on 3 inch. Because indium phosphide still is working on 3 and 4 inch. And so this scanner is capable of handling also the smaller wafer sizes. So you also use the extra wide wafer? No, we use only indium phosphide. Only indium phosphide? Yeah. Really the core of our technology is to build all the functions on indium phosphide.
So what's the bending radius to accomplish the 0.1 dB loss per 90-degree bending for this indium phosphide-based waveguide?
For these waveguides, the minimum bending radius is, I think it's 60 or 70 micron, I think, for this low losses.
So let's give Dr. Augustin applause for his wonderful talk.
Thank you.
Our next speaker is Professor Gerd Moser from Ghent University. He's a professor at Ghent University and also a permanent staff in IMEC. He got his degree in electrical engineering from University of Ghent. His main research interests are in the modeling and characterization of optoelectronics components. And Professor Moser is actually very famous in early work and pioneer work on DFB lasers. He has authored a handbook on DFB laser that was almost 20 years ago. So let's welcome Professor Moser.
Okay, first of all, I would like to thank the organizers for inviting me to this nice workshop. And I hope I can give you some interesting talk on DFB lasers. First of all, I will say a few words and give you a few slides on our research group. So I'm from the Photonics Research Group, of which you can see a picture here. We belong to both Ghent University, Department of Information Technology, but also to IMEC. And IMEC, if you don't know, is a very large, basically microelectronics research center. So dedicated for more than 80% to CMOS processing technology, but they are diversifying more and more, and among others, starting to work also on silicon photonics. And also the group in UGent, which is partly belonging to UGent and partly to IMEC, is mainly focused on silicon photonics. So we are a big group on photonics also. We have 8 professors, 18 postdocs, I have to cheat a little bit. More than 60 PhD students and 8 support staff. Yeah. And, so you see probably only part of the group here. In Ghent, we have clean rooms of about 1,100 square meter, which were built around the year 2000, fully equipped for the 3.5 processing. But as I said, we do a lot of silicon photonics, and as I will explain later, we do a lot actually of 3.5 on silicon. The silicon wafers are processed in IMEC, again using as an Eindhoven, using a deep UV stepper at 193 nanometers from ASML. Recently, we also acquired a EV machine in Ghent, because deep UV lithography can take quite a lot of time before you have all the designs together for a wafer. We also do multi-project wafers. So for fast prototyping, EV is sometimes preferred because it's faster. We also have extensive measurement labs in Ghent, and I don't have a picture, but we have about 15 to 20 different setups for different measurement purposes. And last year we moved to new offices. We were in the center of Ghent, which was nice because you can easily, after lunch break, for instance, go into the city center, go to bank. Now we are outside of the center, but we have since last year new offices, of which you see a picture here. So since we are such a big group of more than 80 people, we have quite a diverse range of research topics, but mainly it's it's based on silicon on insulator photonics, and recently also more and more on silicon nitride technology. Silicon nitride, of course, we do because it's transparent for visible light, whereas silicon is not transparent for visible light. So many applications like sensing, biosensing, we try to move to silicon nitride because you could make use in principle of cheaper visible light sources or cheaper light detectors. Yeah. So we have some basic technology where we try constantly to improve the performances of passive waveguides, where we make photonic integrated circuits. It's passive then, but more and more complicated. The second part of our research is on basic heterogeneous integration technology, and this means that we try to integrate silicon photonics, SOI, and silicon nitride with, well, mainly 3.5 semiconductors, but it can also be, for instance, with ceramics for modulators, or with polymers, liquid crystals for switches and so on. And the idea is, because we have done in the past already lots of heterogeneous integration, but so far it was mainly manually integrating, and we are doing research to do this more automatic, or to have a more industrially compatible integration technology. So as I think for the same for effect photonics, our applications also now are not only applications in data and telecom, but also more and more sensing, so biosensing, gas sensing, Raman sensing, advanced microscopy. I will show a few slides after this slide just to illustrate the kind of things we do, but just a few. The talk I will give today will mainly be on data applications, so we still have lots of activities on high-speed lasers, transceivers, high-speed photodiodes. That's often photodiodes are mainly together with IMEC, so we can do germanium on silicon photodiodes, avalanche photodiodes with very high speed. Modulators is also either silicon modulators, but also 3.5 on silicon modulators. I'll mainly discuss today the laser work, so work on DFB lasers, which allow very high speed direct modulation. And then since a few years we also diversified even more. We have actually every now and then a new young professor, so typically gets a new research topic, and then we started with terahertz and nonlinear photonics. This is mainly aimed at supercontinuum generation, again for future use in sensing. Optomechanics is somewhat special, more fundamental research topic, which gives a lot of publications. And finally, but not least, we have quite some work on brain-inspired information processing, sometimes called neuromorphic computing or optical reservoir computing. And what that is, I will also briefly illustrate in one of the two next slides. So this slide shows an illustration of the work we do on optical biosensing. Basically, we make these photonic integrated circuits containing resonators, typically ring resonators, either in silicon insulator. Now more and more in silicon nitride, because we can use visible light for that. And actually, if you do biosensing with microfluidics, water has less absorption at visible light than at infrared light, so you can typically get better performance for visible light. And then we typically measure the shift of the resonances of these rings or other resonators due to the presence of biological material. You typically need to chemically functionalize these rings, so that's done in collaboration with chemistry departments, so that only certain types of biological material is attached to the ring, and then depending on the concentration you get a shift of the resonance, and that's measured with an integrated spectral filter, and that can also be in principle integrated with photodetector arrays. So far it's been with, actually we mainly use cameras, CCD cameras to measure what comes out of the different filter outputs here, because that's the easiest way for laboratory, but in a real device you could have integrated photodetectors. Okay, so a few more words on the neuromorphic or reservoir computing that we do. This is quite advanced computing. It's a little bit the same as can't think of the name now. Well, what you have is it's a bit like digital signal processing, but then in the optical domain. So we have here a completely passive optical circuit in silicon insulator, consisting of a number of input nodes, which are in our case grating couplers, number of output nodes, and in between you have these you see dense rings. So these are basically long delay lines, and you can have delay lines of various length of various delays. So what we do is we give signals different delays. Then after the different delays, the light is coupled to the fiber, and then of course you detect it, convert into a voltage or an electrical signal, and then you can basically add up the different voltages with a variable weight factor. Yeah? So what we do is with a certain training sequences, we train the weight factors, or we determine the weight factors after the photodetectors to get the optimum output after all the photodetectors in view of the application we want. So for instance, if we want to have a speech recognition, we enter a speech as a training sequence. We then train the network, so we set the weight coefficients such that we can recognize the speech. Okay. So this is all done optically, and actually there's a lot of freedom and it can be very fast, because this is completely passive, and you can choose the delays, very small or very large. The only limit is, of course, in the photodetectors. Okay. And then a third illustration of the work we do is on nonlinear photonics. So here is an example of supercontinuum generation in a nonlinear material. Again, this is 3.5 on silicon, on SOI, so indium gallium arsenide phosphide, which is passive, but it's very nonlinear at 1.55 micrometer. So if you send in a very short pulse with very high intensity due to the Kerr effect in this indium gallium arsenide, indium gallium phosphide, you get lots of nonlinear phase modulation, and that eventually, after some propagation distance, gives you spectral broadening. And as you can see, you can get a spectrum as wide as going from 1,000 to 2,000 nanometers just with an input pulse around 1.55 micrometer. So in this way we work on generating these supercontinuum for sensing applications. Okay, and this brings me to the real topic of my talk. So it's indium phosphide on silicon, heterogeneously integrated DFB lasers. These will be membrane lasers. I think I have a picture here. Yeah. So these are membranes, very thin membranes, maximum 2 micrometer thick, just a few micrometer in width also, that we bond basically with the glue, with a very thin glue on silicon on insulator waveguide circuits, and that we design such that they can operate at they can be directly modulated at very high speed. You see, the grating is fabricated also in the silicon, so that's done with the deep UV stepper. And the rest of the processing, the gluing, or the bonding as we call it, and the etching of the waveguide is done in our own clean rooms. You also see that we have, on each side we have a taper. That's because in the laser part, the light is mainly confined in the 3.5, in the indium phosphide, with a little bit of overlap, of course, with the grating. But then we use these tapers to couple the light from basically the 3.5 DFB laser to the silicon waveguide. And then normally, once the light is in the silicon waveguide, further on we couple it to a fiber using grating couplers. Yeah. So at this point I also want to acknowledge my co-authors, Amin Abbasi, Jochem Verbiest, Mohamed Shaheen, Xenien, Johan Bowlink and Gunther Rulkens. Jochem Verbiest, Xenien and Johan Bowlink are actually not from the photonics research group, they're from a design group, and it's a group that designs very high speed electronics, so drivers, receivers, transimpedance amplifiers. And well, this work was partly possible also because we had their high speed, high frequency characterization experience. And as you will see at the end, we intend to collaborate further with them to improve things even more. Okay. So here's the outline of my talk. I'll first briefly give a motivation for this work and tell you a little bit about potential applications. I'll also give a brief overview of the state of the art, both for not only for DFB lasers, monolithic DFB lasers, but also for other lasers that are used in well, applications are mainly optical interconnects for data centers. DFB lasers have normally the advantage, as opposed to VCSELs, that you can integrate them quite easily together with multiplexers, so they're quite easy to transform into multi-wavelength lasers. If you have DFB lasers on silicon insulator, you also have that advantage, but you have a number of other specific advantages that you can exploit, and you can exploit them especially for getting high-speed direct modulation. Yeah. So I'll explain a little bit what are these specific advantages when you are using very thin membranes, especially for the modulation bandwidth. Then I'll spend some time on the fabrication, and then we'll move on to direct modulation results. But as you can see here, we also have some electro-absorption modulation results. That's actually, if I can go back, that's actually because these tapers here that we use to couple light from the 3.5 to the silicon, if you reverse bias them, normally they are amplifying. If they have a forward bias, if you reverse bias them, they're electro-absorbing. So if you modulate just the tapers, we have electro-absorption modulators. So I'll show some results both on the electro-absorption modulation and the direct modulation that go up to 56 gigabit per second. Our aim is to go to 100 gigabit per second, so I'll try to convince you how we will do that or how we can do that, and then I'll give a summary and an outlook. Yeah, first of all, I also want to acknowledge the 3.5 labs in France, because they were supplying all the EPI, all the 3.5 EPI, and that includes both indium gallium arsenide phosphide and indium aluminium gallium arsenide EPI. Yeah. And especially Douan and Lelarge from 3.5 labs were so nice as to provide us for free with the EPI. So what's the motivation for the work? Well, you probably all know that there's a growing importance of short and medium distance optical interconnects, and especially for links inside data centers, for instance, for connecting servers within data centers, and also for links between data centers. Traffic is more and more determined by this kind of traffic. Yeah. You see here a picture of part of a data center, and you see all the yellow fibers. Yeah. By the way, a few years ago, these fibers would have had an orange coating, meaning that they were multimode fibers, and then most of the transmitters were multimode VCSELs. But big companies like Facebook and Google are more and more transitioning to using single mode fiber with yellow coating. So that means that either they use single mode fibers or single mode lasers like DFB lasers. Yeah, this slide is actually already more than a year old. So at that time, I found out that the market for optical interconnects for data centers was exceeding $3 billion per year. It could be more right now, or it could be less, I don't know. So as you may imagine, traffic in general, data traffic in general is increasing, so also the data traffic inside data centers or between data centers is ever more increasing. But as you see from pictures like that, and you can find very similar pictures on the internet, there are already lots of fibers hanging around or lying around in data centers, so they don't want to ever increase the number of fibers more and more. They also don't want to increase the power consumption for all these optical links or the footprints, but they still want to have higher capacity. So the only way to go to higher capacity is then to have higher line rates per channel. And there's actually a standard emerging, and I think there was some conclusion very recently on a 400 gigabit Ethernet for both long reach, that's 2 kilometer, and extended reach, 10 kilometer. Interconnects, where some of the options are having 8 wavelengths at 50 gigabit per second. That's non-return to zero on off-keying, so 2 intensity levels. Or 4 wavelengths at 100 gigabit per second, again 50 gigabaud symbol rate, but then having 4 levels of intensity, which is called PAM4. Yeah. Some companies also expressed, and especially the big ones like Google and Facebook, an interest in already having a standard for terabit Ethernet. But the bottom message here, of course, is that it's necessary to have transmitters working at least at 50 gigabit per second, and in the future it might be desired or required to have transmitters working at 100 gigabit per second. Yeah. So that's the motivation for our work. That's why we worked on high-speed DFB lasers. A single slide with some overview of the state of the art. So first of all, instead of using direct modulation, you can also use external modulation. The disadvantage is, of course, that you need a laser and an external modulator, so you have a little bit more footprint. Typically also the external modulator will come with some insertion loss, so you either have lower loss at the output, or you have to drive your laser a little bit higher to compensate for that loss. Main advantage of a modulator is that by now actually they have demonstrated 100 gigabit per second, and at the latest OFC there was a post-deadline paper with 100 gigabit per second silicon modulator. But a main drawback is also that they have large power consumption, because you always need these 50 ohm driving lines. So there are a few disadvantages, but they are, it's not denying that they're quite good in terms of maximum bit rate. Then for VCSELs, 56 gigabit per second has been demonstrated at 1.55 nanometer, but that was using feed-forward equalization, so they use special drivers because the 3 dB bandwidth of the VCSEL was below 30 gigahertz. Yeah. Moreover, VCSELs have the disadvantage of a limited output power, and it's very difficult to integrate them into a multi-wavelength transmitter. So it's not so easy to make a 4 times 50 gigabit per second single photonic integrated circuit with 4 VCSELs. That's a lot easier with DFB lasers and DBR lasers. For DFB lasers, 56 gigabit per second was also shown for monolithic indium phosphide DFBs, I think by Japanese one company, I don't remember the name, and also by NtuEE, I think. And last year at OFC there was a post-deadline paper from Finisar where they showed a DBR laser with a 55 gigahertz bandwidth, and they could modulate it up to 112 gigabit per second using the PAM4 modulation format. Yeah. By the way, you could also use coherent solution and use QAM16 or QPSK, but that's a lot more complicated. First of all, you need a local oscillator, you need much more digital signal processing power. So it's also too power consuming and too expensive for, especially for short distance interconnects. Okay, so in my introduction I said that when you have membrane, indium phosphide membranes on silicon, you can take advantage of a few specific properties, or you can exploit a few specific advantages to have high speed or very high speed modulation. Well, I'm going to briefly explain them here. First one is that with these membranes you have very high index contrast, so basically you have 3,5 here surrounded by air, or in practice surrounded by BCB, by a polymer or oxide. And then at the bottom you have a little bit of silicon waveguide, but mostly it's silica. So you have very high index contrast, and because of that you have very good optical confinement of the mode, yeah? Which means you have a very high confinement factor gamma here. This is basically the ratio of the mode confined to the active layer. Yeah? Now this is very important because if you look at the small signal modulation response of a single laser diode, it's a second order response with a resonance frequency, and that resonance frequency, and this is one of the only formulas I will give here, is given by this formula, but you see here the ratio of the confinement factor over the volume of the active layer. So if you have a high confinement factor over volume, then you can have very high resonance frequency. And the higher the resonance frequency, typically the higher the 3 dB modulation bandwidth. But there are more advantages of using a membrane on silica. The second one is that if you do the gratings in the silicon waveguide, again you have a very high contrast, because the silicon waveguide is basically, it's planarized with oxide, so the index contrast is between silicon, which has a refractive index above 3, and oxide, which has a refractive index below 1.5. So again you have very high index contrast. And this allows you to have very strong gratings with very large coupling coefficients. This is especially the case when thin bonding layers are used, and I will show you later that we can have very thin bonding layers down to 10 nanometer. Yeah? So what we have is we have a very high optical confinement, we have a strong grating, and that actually gives you a low threshold gain. Yeah? So threshold gain is total loss here, it's an internal loss plus the mirror loss divided by the confinement factor. Mirror loss decreases with a stronger grating, so high coupling coefficient means low mirror loss. And so that gives you low threshold gain and a low threshold carrier density. Now if you use strained layer multiple quantum wells, there typically the gain is a logarithmic function of the carrier density. So that means if you have a low threshold carrier density, you have a very high differential gain. And remember this formula here for the resonance frequency, it depends on the confinement factor over active layer volume, but it also depends on the differential gain. So now, with this high confinement factor over volume and these strong gratings, we can also have a high DGDN. So that means that most of the factors here are very large, and of course, the current minus the threshold current, you have more or less in control yourself, unless you have too much heating. Yeah? So advantages of membranes is that you can get this number very, very big. Actually, on the next slide, I have some numerical results which were obtained by a student from NTU, Chen Ku Wu, who did a master's student in Ghent and who worked on some simulations of the gain. So the picture on the left-hand side shows calculated gain versus wavelength, but for different carrier densities in the wells. And the increase in the carrier density is every time with a constant number, so you see that for a constant increase, you have much more increase in gain here at low gains than at high gains. And you also see that you get gain over quite a wide range of wavelengths. But this is not more important. What we have here on the right-hand side, this is a more important figure, is this confinement factor over volume of the active layer times the differential gain. So it's not including this current minus threshold current, but almost everything else. And this is, the blue is for 6 quantum wells, the orange for 9 quantum wells, and the yellow for 12 quantum wells. And you see that by increasing the number of quantum wells, you immediately increase this number here, which determines basically the resonance frequency and which determines the modulation bandwidth. Yeah. Especially when you go from 6 to 9 quantum wells, you have a serious increase, and it's a little bit less when you go from 6 to from 9 to 12. Yeah. I should also remark actually that the more quantum wells you have, the more difficult it is to get uniform carrier density in the quantum wells. So we thought that 9 quantum wells was a quite good compromise. You also see that this number increases quite drastically when the modal gain decreases. So if you have lower modal gain, it's even better. That means that you need to have low mirror loss and low internal loss. Of course, if you also have to take into account that you want a certain efficiency for the laser, so you cannot put your mirror loss too low, otherwise nothing will come out of the laser. All right, and then a last slide with some extra advantages of having indium phosphide membrane lasers on silicon waveguides. Well, it's also well known already for a few decades that if you not have a single laser diode, but a single laser diode coupled to an external cavity, you can actually have a second resonance in the modulation response. So one resonance in addition to the relaxation oscillation resonance, which is an electron photon resonance. You can also have a so-called external cavity resonance or photon-photon resonance, and this at a frequency determined by the total length of the external cavity. Yeah. I will show this later. But for this effect to be beneficial, it's important to have a very well-defined external cavity. And that is actually easier also when you couple to silicon waveguides, because silicon waveguides can be very well defined. They have very low loss, much lower loss than indium phosphide waveguides. And so it's quite easy to have a good external cavity in lasers on silicon. And then to end, indium phosphide membranes, because they have very narrow width, have lower parasitic capacitance, and it turns out from our measurements that they have comparable series resistance as monolithic indium phosphide lasers. So that means in principle we can have smaller RC constant or smaller parasitics. And obviously, but that's not so easy, integration with compact low loss passives is possible, and in principle also co-integration with drivers. So it's the last one that is not so easy, but it is possible in principle, and it is easier than with monolithic indium phosphide lasers. So this slide actually shows the typical layout of our laser. So we have here the DFB laser, then normally we have tapers to couple to the silicon waveguide, and then we have grating couplers coupling out to the fiber, and it's between these two grating couplers to the left and the right that we make our external cavity. These grating couplers reflect about 4%. If you calculate the simulated modulation response, you see that indeed you have two resonances. You have your first resonance, relaxation oscillation resonance between 10 and 15 gigahertz, but then depending on the cavity length, you can have a second resonance. It's very important that to have the right reflection for the external cavity resonance, otherwise actually you don't get this nice shape. But I will come back to that later if I have time. Okay, a few words on the fabrication. So we use, as I said already, adhesive bonding. So we bond the 3,5 membranes to the SOI, which is planarized with oxide using basically a glue. It's BCB. We use machine bonding, which gives us a very high yield, close to 100%. And we can make bonding layers as thin as 10 nanometers. And this, I'm not sure it's visible, is shown here on the SAM picture on the right-hand side. Here you see a normal microscopy picture showing the bonded 3,5 membranes on the SOI. Yeah. So as I said, coupling between the indium phosphide and the 400 nanometer silicon waveguides is done using tapers. Maybe I'll, as shown here. And coupling between the silicon waveguide and fiber is done using grating couplers. So on the SAM picture here, you can actually see that I'm not sure it's that easy to see, that we can have bonding layers very thin down to 10 nanometer, and so in that case we have very large coupling coefficients. The tapers are defined by optical lithography, so we are limited to about 500 nanometer, and actually the narrower the taper width, the better the coupling, the lower the reflections from these tapers. Fortunately, our wet etching, yeah, you can see it here. Our wet etching gives a V shape, so even though we have 500 nanometer at the top of the taper, at the bottom of the taper we still have quite a bit less than 500 nanometers, so that means that we in practice have very good coupling, more than 90%, and very low reflections. In the first devices, we actually had one contact on the top, one P contact, so both the DFB and the taper are pumped at the same time. First lasers were also indium gallium arsenide phosphide lasers. That's the epi we first got. And so for our typical lasers, which have a length of 340 micrometer and tapers with 220 micrometer length, we find characteristics like that here. So we get about 6 milliwatts in the silicon waveguide at 100 milliamp, a threshold current of 20 milliamps. That's including the taper current. So if you would exclude the taper currents, it would be a threshold current less than 10 milliamps. And for the optical spectra, you can see it here. We have very good single mode operation with side mode suppression above 40 dB, and actually a very wide stop band, as you can see here. From the stop band, you know, there is a formula that allows you to derive the value of the coupling coefficient. So if you can measure the stop band width, you can immediately relate it to the coupling coefficient. And for this laser, we found a coupling coefficient of 150 per centimeter. Yeah. Some current modulation results for this laser. So this was with single contact for tapers, which act as semiconductor optical amplifiers and the DFBs. Yeah, by the way, this is our typical measurement setup. So you see the fibers here coming vertically, coupling to they come vertically to couple to the grating couplers. This is of course our RF signal, which is combined with the DC signal. And we also water cool the stage of the device so that to keep it at a constant temperature. So first measurement results on the indium gallium arsenide phosphide lasers. This is of course the S21 measurement. You see that there is a 3 dB optical or 6 dB electrical bandwidth of 15 gigahertz. Here you can see that there's a photon-photon resonance present, but it's not affecting the bandwidth, so the modulation response goes down already too much below the external cavity resonance to get to allow it to affect the bandwidth. So nevertheless, we could modulate this laser up to 28 gigabit per second, and here you see some eye diagrams for different bit rates. So here is 28 gigabit per second. The eye is still open, although the extinction ratio is limited to 2.08 dB. Yeah. That's also because our signal generator gives 3 volt, but we have a series resistance of about 10 ohm, and we drive it with a 50 ohm line, so only small fraction of the 3 volt is on the laser diode itself. Here are some bit error rate curves at 28 gigabit per second. This is both for back-to-back configuration and also after 2 kilometers of dispersion sifted single mode fiber. For different word lengths, so for a word length of 2 to the 7, we get a very nice low bit error rates. For higher word lengths, the bit error rate is somewhat higher, but it still stays below the FEC level, so when applying FEC, we could get errorless transmission. The reason why we have problems with larger word length is that actually at low bit rates we have also some special contribution. Here it's not so obvious, but in the next laser it will be more and more obvious. Yeah, we also modulated this laser with PAM4 at 20 gigabaud, 40 gigabit per second. And here you see some eye diagrams on the left-hand side, back-to-back, and the right-hand side after 2 kilometers of non-zero dispersion sifted fibers. Here you see the measured bit error rates. We can still get below the FEC limit, but we have to apply a feed-forward equalization also. How much time do I still have? 5 minutes? Okay. So let's move on to the next laser we fabricated and we investigated. So this was with, I think, much better epi. It's aluminium contanium, aluminium indium gallium arsenide, quantum wells, straight layer quantum wells. When we made these lasers, we characterized them in a static operation. We immediately saw that in the optical spectrum, for instance, we have a much wider stop band. So that means that the coupling coefficient that we extract from it is also larger. Now we have 200 per centimeter Originally we had 150 per centimeter. Threshold current is a little bit higher, it's 35 milliamps, but again this includes current in the tapers, and for the laser itself it's only 15 milliamps. Series resistance here was smaller, 6 ohm. Okay. Now, interesting here is the small signal response, so you can see it on this slide. Now you can see clearly at the higher currents, so these are at 50 and 60 milliamps, but if you go to 110 milliamps, now you clearly see that there's a good photon resonance or external cavity resonance at 34, or that we get modulation bandwidth of 34 gigahertz, not including actually, because we have here also a very pronounced low frequency part, so not excluding this low frequency part, we get a bandwidth of 34 gigahertz. Yeah. The low frequency part we think is due to the modulation of the tapers, because also in this laser there was a single contact for lasers and tapers, so we modulated taper, but they act as semiconductor optical amplifier which have a low frequency cutoff. So we think that the low frequency part is due to the modulation of the tapers. We checked that, so we made the laser with separate contacts for DFB and tapers. We just modulated the DFB part and then we got rid of the low frequency part. Unfortunately for this laser there was a bad connection, a bad alignment optically between DFB and silicon, so no photon resonance could be observed here. Okay, the laser, this one, which has a high small signal bandwidth of 34 gigahertz, not including here the low frequency part. If we modulated it in large signal, we could easily show modulation at 50 and 56 gigabit per second. And you see the eye diagrams here. So they're all for a pseudorandom bit sequence length of 2 to the 7 minus 1. Because if you take longer word lengths, then you are limited by this low frequency part in the S21 response. So left hand side is again back to back, and on the right hand side we have the eye diagrams after 2 kilometers of non-zero dispersion shifted fiber. Yeah. We could actually also, but that's not part of my presentation, I don't have time. You can also apply a thing called chirp modulation, so you can filter after the laser to filter away the chirp, and then you can propagate over many kilometers of standard signal mode fiber. And here are the bit error rate curves for this 56 gigabit per second non-return to zero modulation. So you see that this is again for a short word length of 2 to the 7, so we are not hindered by this low frequency response and the small signal modulation. And so you see that we can get to quite low bit error rates, both at 50 and 56 gigabit per second, and both for the back-to-back and 2 kilometers propagation. Yeah. Okay, I said also that in principle we can have separate contacts for the laser and the tapers. So we in one of the lasers we with FEEP, with focused ion beam, we separated the contacts of the tapers and the laser, and we actually etched down into the top indium gallium arsenide contact layer and a little bit into the top indium phosphide layer to separate the tapers. And then of course, instead of pumping the tapers forward, we can apply an inverse bias. If we do that, obviously the power that you measure at the grating coupler decreases. And so here you see the extinction ratio versus the voltage on the taper for different bias currents to the laser. But you see that we easily get an extinction ratio of 15 dB. This is of course static variation of the voltage on the taper. If we make a small signal modulation, so if we measure the S21 parameter, we find this curve here depends on the voltage over the taper. So if there's positive voltage, again it acts as an optical amplifier. It has a very short or very low bandwidth here. If we inversely bias it, then it's an EAM modulator, and we find a bandwidth of more than 25 gigahertz. So with this bandwidth of more than 25 gigahertz, we tried again to do large signal modulation at 50 and 56 gigabit per second, and that worked quite nicely. Again, this is for 50 gigabit per second, and these upper two curves are for 56 gigabit per second. So they're a little bit worse than for direct modulation, but they work quite nicely. Advantage of this external modulation that we have two tapers, so in principle you could modulate both tapers independently at 56 or 50 gigabit per second and combine the outputs together, for instance in a grating copper. With the grating coppers you can in principle do polarization multiplexing. So we didn't do it yet, but one of the things you could do is we tried to modulate these two separately at 56 gigabit per second, but we did not combine them in a grating copper. We would require a new design for that, but in principle you can make a 112 gigabit per second polarization multiplex signal with that. Okay. So as I said in the beginning, our aim is to go further than 56 gigabit per second, and hopefully we can go to 100 gigabit per second. What you can do further to optimize the laser is the following. First of all, well, you can see it from this formula, which I have been showing already a few times. You need to try to improve this, to increase this. One of the things you can do is to make a shorter laser. But then, of course, if you have a shorter laser, normally the threshold gain will increase. To make a shorter laser without having an increased threshold gain, it requires having a very high, a highly reflecting facet on one side. So our lasers for the moment, they have basically anti-reflection coatings on both sides of the DFB. If you make one of the sides highly reflecting, you can decrease the threshold gain, and so in that case you could also decrease the length of the laser and increase this beta factor here. Yeah. The other thing we will try in the very near future is to use a driver. So far we use a normal driver, but many good results have been obtained with drivers with feed-forward equalization. So in the near future we'll collaborate with our design group, with our high-speed electronics group, to use a driver with feed-forward equalization. That means that you have pre-emphasis at the start of the bit and also at the end of the bit, so that typically allows the laser to operate faster. And it's also planned to have a co-integration of driver and laser, because now also we use 50 ohm lines. The laser has a typical series resistance of 10 ohm, so that means that only about 15% of the signal really reaches the laser. If you have co-integration, you can match the impedances, and it's much more efficient also from a point of power consumption. Okay, so to summarize my talk, at present we have shown current modulation of 3.5 on silicon membrane lasers at 50 and 56 gigabit per second. But the lasers were not completely optimized. There's still a lot of room for optimization, especially making shorter lasers with a highly reflecting facet on one side. Main advantages of indium phosphide on silicon is that you can have very high optical confinement factor and large coupling coefficient, and that gives you low threshold gain and then high differential gain. You also have low parasitic capacitance and series resistance comparable to that of monolithic laser diode, so that means low RC constant. And in principle, you can get a much more controlled external cavity in the silicon waveguide than you can in an indium phosphide waveguide. So it's easier to make use of this external cavity effect. So this is usable normally for transmissions over a few kilometers using dispersion shifted fiber, but if you do chirp management with an optical filter, you can transmit over tens of kilometers. A word on the reliability, because this is of course indium phosphide glued to SOI, and some people might wonder about reliability. Some of the lasers that I have been presenting here, we have been measuring for over a year, or not continuously, but every now and then a few weeks. And so even after a year or 2 years, they still work without any degradation. So they still give the same power, same bandwidth. Okay, I think the rest I said already. So we will try to further improve the lasers by using a high reflectivity facet on one laser side in combination with a shorter laser length. Use a driver with feed-forward equalization and co-integrate electronics and photonics. And hopefully we can get towards 100 gigabit per second non-return to zero on-off keying. Thank you for your attention.
Open for questions. Yes.
Thank you for a very interesting talk. About the photon-photon reaction, you show in one of your slides shows the S21. They seems to pull back at the high current. Yes, this one. What happened at the? Oh, sorry. I think I misunderstand. So actually they kind of kick off around the high current. Yeah. So can we control that process? What happened in between, like a 70 milliamp or 80 milliamp? Thank you.
I don't know, actually, I should ask my PhD students what happens in between. But the second resonance here, you can only see when the first resonance is high enough. If this resonance is too low, then in between it drops too much for the second resonance to be seen. So you first of all need to have this one high enough or close enough to the second one to make them both visible. Yeah. So if you could improve this further, then you can also have this at higher frequency. That's the. Actually, you have a few slides at the end. Yeah. So this is showing the response of a single laser with different external cavities, but with different, all have the same round trip time in the cavity, but with different reflections. Yeah? So you see that if the external cavity is too strong, you actually get something like that. You get these oscillations. This is not good. If the external cavity, if the reflection is too low, you also get something like that. So this is also not good. So you really want to have the right feedback effect from the cavity to make it like that. So it's a little bit of looking for which reflection you have the optimum behavior. Yeah.
You make a 3-phi growing on the silicon, right? Do you make a laser before the glue or after the glue?
No, after the glue. We just glue dyes to the SOI. So we all do the bonding of the indium phosphide. Bonding of the indium phosphide to the SOI does not have to be very accurate, because the processing is done afterwards, and so we can use the lithography accuracy to get the accuracy, the alignment of the 3.5 MESA with respect to the silicon waveguide by using the lithography accuracy and so on.
It's a very good talk. So I have one question. In your membrane laser, although the confinement factor can be increased, so such that all the performance can be improved. However, at the same time, the heating problem may be a big issue. Do you find about this?
Yeah, you're right. The heating problem could be an issue. That's true. But we are working on that also. Actually, we could still improve the series resistance, so we could decrease the series resistance. And one way to do that, for instance, I'm not sure I can show that. Right now, our end contacts are, which are on this thin end layer, are quite far away from the MESA. We want to put them closer to the MESA because we found out that the series resistance is determined quite a lot by the N-type cladding, because it's a thin. Because it's a thin layer, yeah. So half of the series resistance is due to this very thin N-type layer, and our contacts are far from the MESA, so we will put them closer. The other thing we are investigating is that, of course, the oxide here is a bad thermal conductor. So what we are investigating is to use a via through the oxide to the substrate of the silicon substrate to get better thermal conductivity. Actually, right now we don't have so many problems with heating because our probes are thick enough, so they take away a lot of the heat. The probes we use for the contacts, but if you package it, you don't use probes. You have bonding wires, so then you have more problems with heating. But in our experiments, we don't see too much heating, and we think it's because the probes take away most of the heat, because they are, of course, relatively thick metals.
Okay, so
Professor, very nice talk. Yeah, you showed two lasers with different material. One is the indium gallium arsenide phosphide. The other one is the aluminum indium gallium arsenide. And the turns of aluminum gallium indium arsenide with higher speed performance. Is these two lasers with the same dimension and the same geometry? For
well, no, that's
okay. Thank you.
The laser with the gallium arsenide phosphide epi had a somewhat thicker bonding layer, so the coupling coefficient is smaller. It's 150 per centimeter here. For the aluminium containing quantum wells, coupling coefficient is 50% higher, which means it's not comparable. I just gave the two results because we started with the indium gallium arsenide phosphide and now we moved on. And every epi is different also. We also made lasers with Tyndall epi, which we are still working on, so we did not optimize them, but the quantum well numbers are actually around 8, 9. Yeah, we use a lot of quantum wells. Yeah.
Okay. Let's thank Professor Moser for his wonderful talk, and we also thank all of the speakers in the morning sessions. Okay, so this concludes the morning session, and we have lunchbox outside for the students. I guess you can bring your lunchbox back to your lab, and for the I should say the up-campus audience, you can bring the lunchbox to the second floor. The meeting room here cannot we are not allow for food and beverages. Okay, and I will see you at 1 p.m.会当对这边行，嘿，对这行较紧。